Hi everyone. Today we're going to be talking about CFCs, which stands for chlorofluorocarbons. CFCs are not one specific molecule, rather they're a group of molecules that contain carbon, hydrogen, fluorine, and nothing else. So CFCs are chemically inert, non-toxic, and non-flammable, and they are or were primarily used for refrigerants and propellants in hairspray. But since CFCs are so stable, they can reach the stratosphere in their original form. And in the stratosphere, CFCs are broken down by UV radiation, which releases chlorine atoms that destroy the ozone molecules. This led to the ozone hole over the Antarctic. Each CFC has a number suffix that provides information about the molecule. For example, CFC 12, if you just add 90 to the 12 at the end of the code, 90 plus 12 equals 102, and that tells you that that molecule has 1 carbon, 0 hydrogens, and 2 fluorines. In the 1980s, about 1 million tons of CFCs were released into the atmosphere, leading to the ozone hole over Antarctica increasing. So this is a little bit about how CFCs break ozone down. So you can see in step 1 that you have formation of a chlorine radical. And in step 2, you get radical initiation. And step 3, you have termination. However, the impact of a CFC molecule doesn't end there. In step 4, you get radical initiation again to reform the chlorine radical. And in step 5, you reform another chlorine radical. So this continues as a vicious cycle because chlorine-free radicals will continue to form and to destroy ozone. CFCs can decompose with UVC radiation from the sun, but the process is slow. The lifetime of a CFC molecule in the atmosphere is about 20 to 100 years.
Now that we know about the ozone depletion effects from CFCs, let's talk about the negative health side effects that occur from it. UVB radiation exposure is increased with the depletion of the ozone layer, and you might be asking, why is this such a bad issue for us? When our skin comes into contact with UVB radiation, it can cause thymine dimers. This occurs when two adjacent thymines next to each other covalently bond due to the exposure. The covalent bond between the two thymines creates a bump over the DNA, and when it comes down to replicating the DNA polymerase can't accurately read the bump as two separate thymines, and it can create genetic mutations due to an insertion of a different nucleotide that wasn't supposed to be there. These genetic errors make skin cancers and other issues more likely the more errors that are accumulated over time. Another issue we're going to start to see increase more is the development of cataracts, which is essentially the lens of the eye beginning to cloud. This is due to the oxidative damage that comes from UVB radiation and is known to cause oxidative stress, which increases the likelihood of the development of cataracts. It's not just humans that have been impacted by CFCs increasing UVB exposure, it's also been ecological systems. Phytoplanktons, which are very prevalent in the ocean, have been able to absorb a lot of the carbon dioxide in the atmosphere while producing oxygen. The increased UVB exposure has affected the ability for phytoplankton to reproduce successfully. This has led to less food for marine life and a decrease in oxygen production. Since the ban of CFCs, HFCs have been the main replacement for them. HFCs contain hydrogen, fluorine, and carbon, while CFCs contain chlorine, fluorine, and carbon. Although HFCs do not go to the top layer of the atmosphere in the stratosphere like CFCs, they are still potent greenhouse gases that contribute to global warming, which is the trade-off between CFCs that deplete the ozone layer, and now we have HFCs, which increase global warming.
As prior established, chlorofluorocarbons, or CFCs, are the villains in the story of the ozone layer, but their impact doesn't just stop there. CFCs affect a lot more than we might think, especially the ground beneath our feet. When CFCs break down the ozone layer, they let more harmful UV radiation reach the Earth's surface. Now you probably know that UV radiation can harm our skin, our DNA, and things like that, but it also harms the soil. The soil is home to countless microorganisms. These tiny but mighty creatures are essential for nutrient cycling. They break down organic matter and recycle nutrients like nitrogen, phosphorus, and sulfur and help plants grow. So what happens when UV levels go up? For one thing, microorganisms' DNAs get damaged. That's a big problem because it reduces microdiversity, meaning fewer beneficial microbes are left to do their job. It also slows down the microbes' growth and their ability to fix nitrogen, which is key for soil fertility. In fact, the increased radiation creates an oxidative stress, which harms cells and impairs the microbes' ability to survive. And all of this is bad news for plants too. Microbes for symbiotic relationships with plants, helping them absorb nutrients with the UV radiation hurting these interactions. Plants can't get the nutrients they need, which means poorer growth. Now, this doesn't just stay in the soil, the effect ripples through the entire food chain. You see, at the bottom of the food chain, primary producers like plants are crucial. They're the ones converting the sunlight into energy that powers the rest of the ecosystem. But with more UV radiation hitting them, their productivity drops. And when that happens, herbivores suffer. No food means fewer herbivores, which means less carnivores that rely on eating the herbivores. It's like a row of dominoes, which when one of those dominoes falls, it sets off a chain reaction and suddenly you got a massive disruption. In this case, it'd be a lower biodiversity, weakened ecosystems, and even less food for everyone. In short, the ozone layer's depletion isn't just a sky problem, it's a ground problem. So while we're working to protect the ozone, it's important to remember how interconnected everything is. So what's being done to tackle this? Well, scientists are working on more environmentally friendly alternatives like HFOs, which have a much lower global warming potential than CFCs. But they're not stopping there. Researchers are also developing advanced methods to break down the CFCs and HFCs we've already released. Photocatalysts, materials that use light to speed up chemical reactions, are showing real promise. For example, metal oxides, nitrides, and sulfides are being used to degrade these harmful chemicals more efficiently. And polymetric carbon nitride, or PCN, is gaining attention as a particularly effective material in these reactions.